Hi and welcome to another lesson in the physics video series. Today we'll be looking at the centripetal force example of a constant radius with a variable time period. So we'll be actually using the time equation 4 pi squared r over t squared and 4 pi squared mr over t squared, and we're going to hold everything constant and we're going to vary t and see how that affects the centripetal force and the centripetal acceleration respectively. Alright, let's get started. In the given problem scenario, we're going to have a slow turn, a quick turn, and a fast turn. We're going to be using time values. A slow turn of 240 seconds, a quick turn of 120 seconds. As you see, that's half. And then a fast turn. We're going to cut that in half one more time. And we're going to take a look at what a 1,000 kilogram car does while turning on a 10-meter curve. Let's take a look at that math. Here in this problem, we're going to start with the centripetal acceleration 4 pi squared r over t squared, and we're going to insert a 10-meter radius and a 240 second time, and we're going to square that on the denominator, t squared. And when we do the math for this, we get 0.00685 meters per second squared. And if we take the mass of this car, which is 1,000 kilograms, and we multiply it by the acceleration we just calculated, we see we have 6.85 newtons. So a very slow turn requires a very small force. Of course, a slow turn is also a slow speed turn. The long time that it takes to go around means you're going slower, and just like in the last video when we discussed slow speeds require less centripetal force, long amount of time will also require less centripetal force. Let's take a look at a quicker turn. We will halve the time it takes to go around this turn. And in doing so, we get 4 pi squared r over t squared, 4 pi squared 10 over 120 squared, which gives us 0.0274 meters per second squared. We insert that into the F equals ma, and we get F sub c equals 27.4 newtons. So we can see that you've jumped up 4 times. So when we take half of the original time, this t squared is now 1/2 squared. And 1/2 squared is 1/4, which is on the bottom of the fraction. We flip that, we get quadruple. So this 6.85 times 4 is actually 27.4 newtons. And finally, let's take a much faster turn. It takes only 60 seconds to go around. 60 seconds is half the time of the quick turn of 120 seconds. So the acceleration 4 pi squared r over t squared, 4 pi squared 10 meters. We keep the radius the same in all 3 turns, but we change the time. Now it's over 60 seconds squared. A sub c is 0.1096. Multiply that by the original mass, ma, and you get 109.6 newton. And you can see that it takes 4 times more force to hold it into the circle than it did when it was a little slower. So as you go across from example 1 to 2 to 3, the slow turn, the quick turn to the fast turn, you'll see that whatever force you started with, you are cutting the time in half. You are quadrupling the required force to hold the car in the turn. You're going faster, and we know the relationship about doubling the speed is quadruple the force. Well, the relationship also shows us that if t squared is in the bottom and you halve the time, you inverse quarter, which means quadruple the amount of force. And then once again, the same thing. 60 seconds is half the time. So it's time in the denominator, halved it again. So it's inverse half squared. And then, of course, half squared is a quarter. Inverse quarter is quadruple. So whatever we started with back here at the slow turn, we needed 4 times more force when we halved the time. And then when we halved the time again, we needed 4 times more force than the previous one. So this F sub c 109 is 16 times more than the original force. That's because we took half and then half of time again. And so the general relations are quite simple. The more time it takes to go around, the less force required to keep it in a circle. And the less time it takes to go around, the more force required to keep it in the circle. So all the relationships that you've looked at so far, you see force versus speed, force versus radius. If you have a faster speed, it takes a much greater centripetal force to hold an object in a circle. And if you have a longer amount of time, then it takes a much lower force to hold it in the circle. The longer it takes to go around a circle, the slower you're actually going. You see, these are inversely related to each other. This is a parabolic relationship, and this is an inverse squared relationship. And these these general relationships, even though you aren't necessarily solving a math problem, can be easily computed for simple ratios and fractions like doubling speeds or halving speeds, doubling distances or halving distances, doubling times or halving times. To have a good understanding of the ratios is very important because this helps you build your intuition for problem solving. I hope you enjoyed this video and you now see the differences between the different variables and their effects on centripetal acceleration and centripetal force. Thank you for watching, and I'll see you in the next video.